All right, now we are going to finish up chapter 7 by talking about 7, 8 and imaginary numbers. Mathematicians just could not have enough fun with real numbers, so we decided to create imaginary numbers to deal with some of the things that we couldn't understand. So remember, we used to say that the square root of a negative 9 was impossible. We couldn't do it because we can't take the square root of a negative, because nothing times itself would equal a negative, right? But we still need to be able to work with some of these negative roots or roots of negatives. And so what we've defined was that the square root of negative 1 equals the letter I. So if the square root of negative 1 equals I squared equals I times I, which equals the square root of negative 1 times the square root of negative 1, which equals the square root of negative 1 squared, which equals negative 1. So all that you need to gather from this is that the square root of negative 1 is I, and I squared equals negative 1. So after you get that, there's lots of little things that we can do. For example, let's go back up here. The square root of negative 9. Well, I know that's the same thing as the square root of negative 1 times the square root of 9, right? So, square root of negative 1 is I. Square root of 9 is 3. So that equals 3i. Okay? Square root of negative 25 equals square root of negative 1 times square root of 25, which equals I times 5, which equals 5i. Okay? Let's try a more complicated one, the square root of negative 12. Well, I know that's square root of negative 1 times the square root of 12. And here I can break that into 4 and 3 and 2 and 2, right? And so a 2 comes out. So that's going to be 2i times the square root of 3. Okay? So that's the process. Now let's do a couple problems. So the square root of negative 2 times the square root of negative 5. This is very important. You cannot just multiply what's inside, because if you just multiply what's inside, then it denies the fact that we're originally trying to take the square root of a negative. Okay? So you cannot just say, oh, that's the square root of 10. That is not true. Okay? What you have to do is break it up. So this would be square root of negative 1 times the square root of 2, square root of negative 1 times the square root of 5. Okay? So that would be I times the square root of 2 times I times the square root of 5, right? I times I is I squared times the square root of 10. And what is I squared? I squared equals negative 1. So negative 1 times the square root of 10, which equals negative square root of 10. Okay? So let's do another one. All of the rules of distribution and double distribution and foiling, they all apply the same way with the I. So let's say negative 4i times 3 minus 5i. Okay? So this times this and this times this. Negative 4i times 3 would be negative 4i times 3 minus negative 4i times 5i. Okay, now this is the thing to watch. There's a lot of negatives going on, so you want to be really careful about using your parentheses and staying organized. Okay, negative 4 times 3, okay, it's going to be negative 12i, and then minus negative 20i squared. Okay? Now, I squared, right? That's the same as negative 1, so let's rewrite that. Minus negative 20 times negative 1. Okay? But a negative times a negative is going to be a positive 20, right? And then we can distribute this negative in. So negative 12i minus 20. But in the complex, this is called a complex number because it has a real number and an imaginary number. We're going to write that in this order. Just like that. Okay? Let's try another one, but this time let's FOIL. 5 plus 7i, 5 minus 7i. And you might recognize this as a difference of squares factorization, but let's take it old school and do the foiling. So 5 times 5 is 25. 5 times negative 75i is negative 35i. 7i times 5 is positive 35i. And then 7i times a negative 7i. A positive times a negative is a negative, right? 7 times 7 is 49. I times I is I squared. Okay? Now these, in this special situation, are going to cancel, right? Because a negative 35i plus 35i equals 0. So I've got 25 minus 49 times negative 1, right? Which is the same as 25 plus 49, which is the same as 74. Okay? So you can see how the process is really similar to ones that we've done in the past. Now, remember how we do not like radicals on the bottom of fractions? Well, we don't like complex numbers on the bottoms of fractions either. So let's talk about fixing that, okay? So I've got an imaginary number on the bottom, but I don't want to have an imaginary number on the bottom. So what could I multiply this by to get rid of this I? Well, if I multiply an I by another I, then it turns into a negative 1, and there's no more I. Okay, so I'm going to multiply it by I down here, and if I multiply it on the bottom, I have to multiply it on the top. So this becomes 7i plus 4i squared over 5i squared. Then we change those I squareds into negatives, so 7i plus 4 times negative 1 over 5 times negative 1. Okay, I'm going to move down here, and then I have 7i minus 4 over negative 5. Remember, I like to keep this in order, so negative 4 plus 7i over negative 5. And I could factor out a negative on top. Notice how I changed that to minus 7i divided by negative 5. And then those cancel out. So my final answer is 4 minus 7i over 5. Okay, that wasn't the worst. All right, let's try a different one. Negative 2 plus 9i over 1 minus 3i. Okay, now, whenever you try to get rid of a complex number on the bottom that has two terms, just like when we're dealing with radicals, you're going to multiply it by its conjugate. Okay, so the conjugate in this case would be 1 plus 3i. If I do it to the bottom, I have to do it to the top. Okay, see what I did there? I just changed the negative to a positive, and I'm multiplying by its conjugate. And then I'm going to FOIL the top, so negative 2 times 1 is negative 2. Outside, negative 6i. Inside, 9i. Last, 27i squared. Okay? And then, let's do the bottom. 1 minus 3i plus 3i, right? Minus 3i and then plus 3i. And then minus 9i squared. Okay? Let's rewrite this, make it a little bit more simple. Negative 2. Then I've got plus 6i minus 6i plus 9i, so plus 3i that I squared is a negative, so minus 27, right? Because that's a negative 1 times 27 is negative 27 divided by 1. Negative 3i and positive 3i cancel out. Minus 9 times negative 1, right? So that equals negative 29 plus 3i divided by negative 9 and negative 1 make a positive 9, so it's 1 plus 9, which is 10. And that's it. I'm done. So the last thing that I want to talk about is if I equals the square root of negative 1, then I squared equals negative 1. So I cubed would equal I squared times I, right? Which would equal negative 1 times the square root of negative 1. Okay? Now, we can use this to consider what really large exponents of I would be. Okay, let's try it small. I to the 7th. Okay? Let's change this to I to the 6th times I. Okay? So I'm allowed to do that, right? Because of my rules of powers. And then I can say that's I squared to the 3rd times I. Well, what's I squared? I know that's negative 1 to the 3rd times I. Negative 1 to the 3rd is negative 1 times I equals negative I. Okay? And you can use that same process to do I to the 75th. Okay? Looks daunting, but it's not. I'm going to first make sure it's an even up there so I can divide it by 2 like I do here. So I to the 74th times I. Okay? Then I'm going to divide it by 2 and see how many I squareds I have. So how many I squareds do I have? Well, that's 74 divided by 2, which is 37 of them. That's a lot. Times I. Okay? And then I squared equals negative 1 to the power of 37 times I. Okay? Negative 1 to the power of 37, because it's negative to an odd power, it's going to end up being negative 1, right? This is negative I. And then finally, I'll show you one that's even. Let's just say I to the 36th. Okay? Well, that's the same as I squared to the power of 18, right? So negative 1 to the power of 18. And what's negative 1 to the power of 18? Well, since this is even, it's just going to be positive 1. Okay? And that's how you can do all of these. All right? Yep, that's it.